Hello, I am Emmanuel Markoulakis from the Hellenic Mediterranean University. I'm doing this video because some creators of YouTube have come with some new information about what the title is, the central title concept is, what the Ferrocell really shows. And in my opinion, they present some incorrect information from my research. And it's a good thing, I remind everybody, that when people which are not immediate experts on these fields, academic experts on these fields, doing such kind of videos, it's always a good thing to state that these are all under their opinion, yes, and exactly the same I'm stating also here, that this is my opinion, okay. I don't want to have any misconflict with anyone, yes, but I am obliged, because my research all these years, my experience, to set some things straight. So we will now see what is presented. I use material from the video of these creators, but this is under fair use because I'm reviewing this material. So let's see now what. Okay, they use here this paper published 2020, where the researchers here have developed a software package for visualizing magnetic moments, and therefore the field of magnets, permanent magnets, but also fields from electrical coils, and so on. The citation of this researcher is here, are these people. And what they did, they use classical analytical electromagnetic theory and simulate magnetic moments here, visualize magnetic moments, where we have here rods which are aligned to external magnetic field, and here we see actually the alignment of these rods under an incident field of a pole of a magnet. So the lines are going all in here in the center point, they dive in, and therefore also the ferrocell has, because these lines are becoming here vertical, they minimize the surface, and the light scattering is now minimum, and therefore also the ferrocell depicts these areas as black, this area. So here is the torus, which is formed from the polar field of a magnet of one pole, and we see here all the moments here of these nanorods going in. The same is actually happening on the ferrocell, which has nanoparticles, 10 nanometer in size, and they are forming a few hundreds of nanometers of these rods, nanoneedles or nanorods. However, here the creators say that this film is very thin. This is true. This is 10 microns thin, and therefore from there they imply that this is actually only a 2D surface, which is true to some extent, that it's a 2D cross-section projection of the field, of the incident field on the ferrocell surface. But there is some difference, because the nanoparticles are 10 nanometers, and the thickness of the film, of this thin film of nanorods, is 10 microns. So in the new generation of ferrocells, in the older on the older generation of ferrocells, it was 25 up to 50 microns. So actually, for a 10 micron thick ferrocell film, which is a super paramagnetic film, an analogy is a man 2 meters in height, and the whole thickness of the film is 2 kilometers. It's 1,000 times more. It's the nanoparticles are 10 nanometers, and the thickness is 10 microns. So it's 1,000 by a factor of 1,000. So this is not to scale. So you now imagine that there's actually plenty of room here to actually, yes, it is a 2D. It is a compressed field from 3D to 2D, but actually there's plenty room to make an imprint, a 3D imprint, compressed of course to 2D, but not exactly flat 2D as we have in an iron filling experiment. So it's a compressed 3D field into a 2D. It tries to make a 2D compression, but it's not totally 2D. You can't actually compress here this 3D field in this 3D space. So it's macroscopic. Yes, it's 2D for an observer, but for the particles, from the reference point of particles, of the nanoparticles, the 10 nanometer inside particles, there's plenty room to compress the whole 3D field here in this 3D space. So keep that in mind as a first point. So the field now is here. It's not really 2D, but it is compressed. It's a 3D field compressed in a very thin layer, but still it has a third dimension. Yeah? And that's why the ferrocell, we will see later, please stay with me, we will explain everything, has also retained depth of field information, together with magnetic transparency, which is very important to understand what the ferrocell shows is exactly what is predicted by theory. We will prove that in a few minutes. So, firstly, to say that this creator is saying that the ferrocell is not showing magnetic lines of force, therefore it's not a sensor, a magnetic sensor. To say this, firstly, we have proven this with actual experiments, not simulation, that the ferrocell is showing correctly with 2 different experiments a magnetic flux as predicted by theory of the homogeneous field between the poles of magnets, and also the homogeneous field inside a solenoid. So to say that it displays correctly the magnetic field of lines in these cases, but not in ferromagnets, is absurd. Yes. Secondly, we are not sure that the input at this specific simulation used is correct, because first, the density here is too large, it's ridiculously large. In a normal ferrocell, the volumetric percentage of the nanoparticles compared to the solution which they're in is 0.2%, 0.2%. So the density is very high here used, and we cannot know the exact paths of the trajectory the nanorods are taking, because you see the nanoparticles, which are spherical, are joining and forming these nanorods. The nanorods are about a few hundreds of nanometers long, but the nanoparticle itself are only 10 or less nanometers. So we don't know exactly what the trajectory is, the path they are taking, because this simulation seems to just to input classical magnetic moments, and I'm not sure if the simulation also takes into account the magnetic anisotropy of the nanoparticles, which then will give different field pattern. So first, the density is too high, so the simulation is not correct in that point. And also the creators say that the nanorods they use are 200 times larger than the actual used inside the thin film of the Ferrocell. So we have this. You have also take this into account. We see here a video of the nanoneedles inside the ferrofluid, how they align to an external magnetic field, and also the light scattering effect. But we are not sure. We cannot be sure about the. We can zoom in individual nanorods, but we are not sure about the final trajectory the magnetic flux ligands are taking inside the ferrofluid. And yeah, so the simulation therefore is under question because the lack of input data. But in general, yes, the lines are going this direction to the center of the pole. So we have the pole now under here, under the surface. Here is the center of the pole of the magnet, and the lines are going this direction. But again, we are not sure if this is the exact pattern and if it doesn't make any other trajectory, the lines here, because having so much dense nanorods simulated and in that large size makes the behavior of the ferrocell now more to the macroscopic side, which means that there is a lot of coherence. And we know that the nanomagnetic thin film of the ferrocell has a quantum behavior. So the larger you make the simulation, or with more large nanorods and with more dense nanorods, it becomes more macroscopic. So it's now not so high fidelity, your simulation. So you have to input the correct density and also the size to be sure. But for the sake of discussion, let's say that this is accurate. Let's assume that this is now accurate. So the creators now are simulating here the nanoneedles with the pole of the magnet, one pole of the magnet under the surface. Here the lines, the nanorods are diving in, and their surface is becoming less because they're becoming more vertical, and therefore there's less light scattering. And that's why in the ferrocell the center of the pole appears black. So what now the creators are arguing is this here point, which I disagree strongly. This point with which I disagree strongly. They use next this pattern obtained from the simulation and use it inside Blender, and they put here a point light source. It's not a laser, but it's an incoherent line, but nonetheless is a point source emulating an LED, because in a ferrocell you have an LED ring, an LED strip ring around here, 360 degrees. And they say that the ferrocell does not show any magnetic lines of force. They just show specular reflections. So here we see illuminated the surface of the torus here. And because there are point sources here, if you add and rotate this image 360 degrees, you get the familiar wireframe pattern of the ferrocell with the crisscrossing lines, and these are not magnetic lines. So that is the argument of these creators, which is bluntly wrong, and I will prove that now. First, it's not good practice to use only one light source. You need to Ferrocell to operate and view each line, each magnetic flux line from every angle. You need a homogeneous uniform lighting 360 degrees. Else you can come to wrong conclusions. But even so, I will now show you what really is happening, in my opinion. We see here the blender image, the blender image the creators used with a simulated torus of the thin film, and it is the surface of the torus. The perimeter is illuminated by the one light source here, and actually it reaches as far as here. If you make more intense the light, then more areas of the torus bulk, the torus perimeter, will be illuminated, which is not the case we see in the Ferrocell. The Ferrocell, the lines that displayed stay at place as we increase the intensity of the LED lighting. The lines positions do not change. Here, as you will increase the light source, more and more of the surface of the torus will be illuminated. So keep that in mind. And we see here also this here, which is not does not match with what we see in the Ferrocell. In the Ferrocell, the area here is dark. It's not lighted up. So blender, which is not does not take any magneto-optical effects attributes. It just shows how light scatters in curved surface and reflects. Yes. So this is inconsistent here with what we see in the Ferrocell. Actually, also, they shouldn't have, it was not needed to use all this simulation by MacPyth the program. They could have used just a solid surface torus. The effect will be the same. The LED illuminating the surface of the torus. So here is now the image under question. They make here, the creators of these videos made a side-by-side comparison of the actual display of the Ferrocell with a magnet pole under the Ferrocell and one light source on the perimeter with what they get from the blender simulation, let's say so. Yeah. So what they actually did is they shifted here the blender image. They displace it in order to match to the left here. They displace to the left to match what we see here on the actual image of the Ferrocell. Of course, with one LED source, you will not see anything of that image here displayed of the Ferrocell. Thanks God, the light here is diffused on the perimeter of the cell, and that is the only reason you can see this. Because if it was just one light source, I assure you will not see anything of this loop here. So this here, this is actually the edge of the cell. This is an actual photo taken by the experiments done by the creator of this video. But this here now does not match what we see here. It doesn't match. We see here, you see, that here in the blender is only the perimeter of the torus lighten up. Yes, but here the line is attracted here. The whole line here loop is attracted to the center of the pole. Also remember we have also some depth of field information. So this is inclined here. So this makes this line here, this loop, makes it automatically a magnetic line of force, since it is attracted here to the pole, and it's not just outlining and lighting up the perimeter of the torus. Let's this line instead is attracted to the center of the pole. So it's automatically, we can say it is a magnetic line of force. It cannot be anything else. So you see, in order to understand, when we use a straight homogeneous field of a solenoid to display it with a ferrocell, or the homogeneous field between two attracting poles of two magnets, where we have straight lines, it's much more easier. But with ferromagnets, when we display the incident field of ferromagnet to the lens, to the surface of the cell, because we have a curl, yes, things are getting more complicated. But it is all a matter of understanding how the field is compressed on the 10 microns thickness of the cell, yes, how the 3D image is compressed in this thickness, and how it is projected. It's very important. As soon as you understand these two things, you will see that actually the ferrocell depicts exactly what is predicted by theory. So stay with me, please. So this line now here, this is actually a loop. Remember, I told you that when you see the field in the ferrocell, even with this single light source, which again I say it's wrong, you need homogeneous 360-degree lighting. Every magnetic line or loop must be illuminated from all angles, else you can make wrong conclusions. But for the sake of the argument, I will use just this experiment to prove that even with this experiment, with this single loop, the ferrocell shows correctly the field. So remember that I said that the ferrocell shows depth of field information. So this is not just flat here in a 2D parallel surface, but it's going it is inclined here. So it shows depth of field, and in the same time has also magnetic transparency. When you see the magnetic field and magnetic flux lines on a ferrocell, you see the lines going through both, around and through both of the poles of the magnet. So this here, what you see actually here is this here. So here is the ferrocell, and we have put a pole of the magnet under and perpendicular to the surface of the ferrocell, a pole of the magnet here. And what this here represents going around is one loop here. Is one loop of the magnetic field, which is attracted here, all going here to the center of the pole. So you see, even with one light, because it is diffused here, and that is a good thing, because it's diffused on the perimeter of the lens, we can see one loop of the magnetic field going around, retaining depth of field information and magnetic transparency. You can see the magnetic loop here, going around both poles of the magnet. You understand? So this is astonishing. Yes? So this is made even more evident here in one of the action labs, the famous YouTube channel, Action Lab. We made experiments with do-it-yourself ferrocells, with rough ferrocells, very thick glasses and large and square. And also he used LED strip as lighting, but because the surface here is very big of the cell, and it's far away, the light is very well diffused. And we can see here exactly what theory predicts. We will see here, we have here the classical field of the magnet, and here we see the projection is exactly what we expect. Here is the ferrocell. Okay, here we put the magnet above the ferrocell, doesn't matter if it's above, if below. So we here now, in this particular here magnetic field imprint, the observer, imagine you are here inside this cage and you look up and you see the lines from inside, from within the cage to the upper side. So you see here this line exactly as theory predicts. Of course, there is a point here we will explain later, because I contacted Action Lab and asked him where is the pole on the magnet, and he told me that the pole is in the long side here. It's not in the short side of the magnet. We will explain this actually what the cell is doing. It's taking here the field going here and flips it 90 degrees and projects it to a flat surface. It's like mirroring your face on a mirror. You will still see your face. Yeah, we will explain this in a moment. So we can say here in the case of Action Lab that this is a very rough ferrocell that is more like to the macroscopic operation, because he uses very thick glasses, maybe probably half a millimeter thick, and it's enormous. The cell is enormous, and of course the ferrofluid is not diluted. It's very little diluted. It's not it's not like the actual ferrocell, which is very heavily diluted. And so the thin film layer is not 10 microns or 20, probably it's 100 microns thick. So this is more to the macroscopic side of behavior. It has a lot of coherence. But we see here what is going on. So the pole here is this long side, and it's nevertheless it gets projected here, flipped and projected. Here is the ferrocell surface. Here is the magnetic field, as on the way he is holding here the magnet. So here is the pole, which is the long side, and the field gets flipped and projected nevertheless again on the cell surface. So we come now to the center of this presentation. So please stay with me, because now it's very important. We have seen now that it's not actually a hot spot light effect of the ferrocell reflecting on the surface of the torus formed by the nanoneedles, but these are actual magnetic flux lines, and actually they are magnetic loop lines. So you see the whole field passing through the whole flux loop, passing through the ferrocell surface. So we see here, this is the profile view of the ferrocell on its side, and we see here the loops of the magnetic field penetrating perpendicular the ferrocell thin film, yes, which is inside here between the two optical glasses, which are in the latest ferrocell just a half millimeter thick. So the total thickness is 1 millimeter in the mini ferrocell series. So these lines now are passing here in. We can see this in this image also here. And now the whole 3D actual field, the spatial on the air, the classical field of the ferrocell is compressed inside the room here of the thick film. So it's not just a 2D plain flat 2D projection. It is compressed from 3D to 2D, but it's not 2D, absolute 2D. It has a thickness here. So it's actually a compressed image, not totally compressed 3D field imprint, magnetic field imprint, not totally 2D compressed magnetic imprint of the actual field. So we have some depth of field information, which the ferrocell shows. So imagine now what happens if you compress this field here in this small space. What an observer, a macroscopic observer, will see. What is happening, and this is actually, it is my opinion, and is active research, because we are still researching the vorticity we see in ferromagnets, because the ferrocell, as I've shown in my experiments, and I will reference this later, these experiments shows the net nanomagnetic field inside the bulk of the matter of the magnet, and not the classical outside field. And we have done experiments with gyromasking for magnetic shielding, which proves exactly this point that in order to see the field of the magnet must be, the bulk of the matter must be present. We did that with a ring magnet. We shielded only the bulk, and we left the air cap of the ring open, unshielded. And when we have done this, we didn't see any field at all, which is normally not the case, because even so, the cell should pick up the field on the air cap of the ring magnet, but it didn't. Yeah. So you have to keep that in mind, please, that the Ferrocell is a quantum device, meaning nanomagnetic. It has nanomagnetic sensors, a few nanometers in size, and that makes him to behave as a quantum sensor. And it senses directly the nanomagnetic moments inside the bulk matter of the magnet. So this is an active research. We're not sure about the vorticity. I mean, that these loops are not just straight, but are actually vortexing in. Yes. And we have to say here, an ellipse is anyway a vortex motion. Yes, because the radius is not the same. It differs. So it has actually, an ellipse has a vortexing action. And yes, but for the sake of this discussion here, let's say that we explain this now macroscopically. We explain the Ferrocell, what we see in the Ferrocell, purely macroscopically. But I must also insist that this is active research, and we are not, we cannot claim final conclusions about what is really happening inside the field of a condensed matter magnetic material. Yes. So what happens now is, imagine this line here laid on the Ferrocell surface on its side, like this. So because the whole field is now 3D compressed here, 2D compressed, but not totally compressed, it still has some 3D information. These lines which are going, the plane of these lines which is going vertically, imagine now that these lines are horizontally projected. So when you do that, the loops here, the magnetic loops, because we say, I remember you again that in a Ferrocell, it's not like the plain, flat, poor picture we get with iron fillings, which is just, and many people are very familiar to this and cannot think of anything else. So the Ferrocell has also depth of field information, has actually, it's a compressed 3D image, but not completely compressed to T print, to a 2T imprint of the field. So that makes the whole confusion. And to understand what the cell shows is to understand how the field is compressed inside this narrow, very small thickness here, and how it is projected, the angles of projection of the incident field to a flat surface of the cell and a thin film. So now these lines are not going vertically in, but actually are lying here horizontally. And if you do this, the loops now, we have previously shown, the magnetic loops looping here, and because the magnetic transparency, we can see both poles, the flux going through both poles and looping around the magnet in a Ferrocell display. Now we see this pattern here. Also remember, keep also in mind that magnetic flux lines are everywhere. If we see just 10 magnetic lines on a Ferrocell, or 53 magnetic lines of force in an iron filling experiment, this does not mean that in between there are no magnetic lines of force and magnetic loops. They are everywhere. Every conceivable small area, as small you can imagine it is filled with magnetic lines of force. And if you sprinkle more iron fillings, you will see more and more magnetic lines of force forming. Yes, so remember that. But because the lighting only the lines which are in the direct scope of the view of the LED are intensified and lighted up more intensively. So that's why you don't see an enormous amount of lines, but you see a finite number of lines in magnetic loops here, specifically. Yeah, because if you illuminate it fully, then you will see probably so many lines that you will not get the wireframe, the discrete magnetic flux lines display on the cell of a magnetic field. But instead you will get, in this case, a cloud image. The same we get also with squid scanning magnetic microscopy. And also, if you put one light source, incoherent light source, at the center of the cell, you will get again, because now the lighting is uniform, but also gradually, it's going gradually out, you get again a cloud image, and you cannot see discrete lines. But if you put lighting 306 degrees around, you get the wireframe image. So now we explain how the lines are actually laid horizontally and not are projected horizontally on the surface. You can understand also how this brings us to this image here. Yes, how now here is the cell. Yes, and now because the lines here are projected horizontally on the surface, you can understand this how we see the final image of the pole of the magnet of the cell, which is actually both poles. We see the fields, the loops going around both poles. So here is the top view here is one magnet, and below here under is the field of the other, and the flux lines of the other pole of the magnet. So it's like squeezing the whole field in this narrow part. It's actually not different from a toroidal flux. You see, in a toroidal flux, here's the top view of the toroidal flux, because the complaint here that this is not correct, we see here crisscrossing, but it is actually you are not very familiar when seeing wireframes, 3D wireframes. So this is a wireframe with a depth of field of information and also magnetic transparency. So you see the lines or the loops going through both of the poles with depth of field information. And it's actually the same with the toroidal flux. The toroidal flux, we see here this crisscrossing, you see? You can see the crisscrossing, but you know that the toroidal flux is actually concentric straight loops, but still you can see the crisscrossing. Doesn't mean that the lines are touching with each other, because this is not allowed from a classical theory. But they are not crisscrossing; they're overlapping in 3D space. There is a space, a distance here between. But you can see here the crisscrossing, and here also a top view. Even if the lines are going as straight loops, as we have here, yes, we still can see the crisscrossing effect. So you understand now that how more rich the display of a magnetic field with a ferrocell is compared to the flat iron fillings magnetic imprint. And this is even more evident why this crisscrossing happened, because you remember the actual 3D field in space is compressed on the thickness, inside the thickness of the cell, the only 10 micron thickness. And we can see here, now where we compress the toroidal flux, this gadget, we can see evident this overlapping crisscrossing lines. Yes? So I believe now that you are all convinced that this is not the case of a hot spot LED spectral reflection effect, yes, but this is actually a magnetic line of force, a magnetic loop going through both poles displayed, and we get the full effect when we have used 360 degrees lighting on the perimeter, uniform lighting, homogeneous lighting on the perimeter of the lens. And besides, we have proved with our experiments, actual experiments, not simulation, that it shows the magnetic straight lines of homogeneous field inside an air solenoid and between the two attracting poles of two magnets. So why should it show any different? You cannot say that it shows magnetic lines of force in one case, and in another it does not show, but shows some kind of imaginary reflection. Doesn't make any sense. The only thing is, again, I repeat, to understand that now when we project the incident field of a ferromagnet, because we have not straight lines now, but we have curved lines, things are getting more complicated, and it's a matter now we see not just lines but loops, magnetic loops, looping between the poles and retaining and the ferrocell retains the depth of field information and also magnetic transparency, meaning you can look the flux going through both of the poles of the magnet. Yes, why shouldn't it show any different? There's no work around this. Yes? Okay, let's continue. We will finish in a few minutes. Here we see the field, the total field, the magnetic field, as top up from a top view. We used a ring magnet. So what the ring magnet has some special feature. The whole field, the whole 3D spatial field of the magnet is confined inside its ring hole, inside the hole, the air cap. So we can now, especially for ring magnets, we can get beautiful pictures of the whole field of the magnet. So you remember, we see its top view of the whole torus now, the whole torus field, the compressed field of the magnet as with depth of field information. So now you see it's actually this here. It's actually this here. We see the field, but now because it is compressed, in the thickness of the lens, we see this torus, this overlapping here lines crisscrossing, but they are not actually crisscrossing, they are just straight loops. And you can see this very beautiful field of the whole torus field of the magnet. Here, where the hole is, it doesn't mean that there are no magnetic flux lines. On the contrary, here the magnetic flux lines are the most dense, but because they're going totally vertically in, the surface is minimized of the nanorods, and therefore we get minimum to zero light scattering. So that's why we see the area black, but it doesn't mean that this area here is void for magnetic flux. It's full with magnetic flux, and actually it's the most dense magnetic flux. Okay. This concluded this presentation here. Thank you very much. I believe I have enlightened you with what is this truly amazing new quantum magnetic flux viewer device shows, physical device. I remind you that it is a physical device. That's why it has to obey physical rules and laws. And the dominant phenomenon on this device is driven by magnetism. It's not a random optical effects and so on. It's 100% a magnetic sensor with very rich display, compressed cross sections of the field of the incident of an incident magnetic field with depth of field information and also magnetic transparency. I understand that people are indoctrinated, but some with quotes indoctrinated with the iron fillings experiment, which is a 200 years old experiment. It has a very flat, poor representation of a magnetic field. But this here, I believe, is the new modern iron fillings experiment, which is happening in a nanomagnetic level. It is a quantum sensor, therefore, a quantum magnetic flux viewer. Thank you very much. So, I just want to say as a last word that my purpose is not just to come in conflict with some people, but anyway, because my experience on this field, almost 4 years now, I'm researching this matter, and the research means actually is an ever-going process of refining your conclusions and adding and modifying. And I regard this information to go out. And YouTube for me is not a place for making scientific research. However, because many people are influenced by YouTube channels, we must be very careful. And I repeat again, we must be very careful and not to try to enforce scientific consensus through these videos. So it is good thing in the beginning of each video or in the description for a creator of YouTube to state that this reflects the personal opinions and not make any definitive claims. The same is also true for this video here. These are my personal views and opinions. However, they are based on an extensive research, 4 years research on this particular topic. I thank you very much for listening to me. Bye. This is Emmanuel Markoulakis from the Hellenic Mediterranean University.